Hi to you all. I hope you had a nice break. Now, I've just been asked about question 13 on the second exercise, and so it isn't like one we've done before, which is fine, but it's applying differentiation to context. So differentiation is all about rates of change. So here we're considering the cost of polishing the surface area of a cylinder, and you get this information about how that cost is going to be applied. So it's £2 per curved surface area plus £3 per centimetre square of the circular top and base. So there it's telling about the surface area of a cylinder. The curved surface area is the circumference of the base times the length, and obviously the base itself is just pi r squared, and there's two of those. So I've actually written this out. I've sent the mark schemes out, but I'll talk you through it anyway. So the other key bit of information is that the volume is given to us as 75 pi. So if we know that the volume is pi r squared times the length is the unknown quantity. We want to have the length in terms of r, because the thing we're trying to show for the cost is all in terms of r. There's no L in here. So pi r squared L equals 75 pi. That's what we're told. Therefore, L as a rearrangement of this must be equal to 75 over r squared. The cost is two lots of the curved surface area, which is 2 pi r times L. We've just shown that L in terms of r is this. Add 3 lots, so £3 per centimetre squared of the base and the bottom, or the top and the bottom base. And so that's pi r squared for each of those, which is 2. And so we get this. And if you simplify it carefully, it does just work out. So 2 times 2 times 75 is 300. One of the r's cancels, and you've still got the pi. And then simply 6 pi r squared. Now, it's asking for the minimum cost. So normally we have some y in terms of x, and we get dy by dx. Here we've got c cost in terms of radius. So if we are interested in the rate of change of cost against radius, when we differentiate, we'll get not dy by dx, but dc by dr. So dc by dr is this, and the minimum of c, just like the minimum of y would be at dy by dx equals 0, the minimum of c will be at dc by dr equals 0. And to show it's a minimum, we use the second derivative and show that for that particular value of r, it's greater than 0. Now, actually, I did that before reading the next part of the question, so it's that this comes into it in part C. So, got dc by dr here. Solve dc by dr equals 0, like so, and you get r equals cube root of 25. So it's for that radius, you get the minimum cost under these conditions. And so substituting in r to find c. So this is just like putting the coordinate of a turning point into the original equation to find its y coordinate. But here it's not coordinates, it's radius and cost. And we get an answer to the nearest pound. And then so the part C is, here we are, it's second derivative. To verify that this is a minimum, we would find the second derivative and plug in that value of r, and if it's a positive value, it means it's a minimum. So that'll do. Okay, cheers.